So our goal right now is to look at some basic commands in reg class and also this step function. So the first thing you'd want to do is load up reg class. Now inside of reg class is a data frame called survey10. And I've already loaded this up, but we'll load it up ourselves here. And now we've loaded it up. If it doesn't work, make sure you have reg class going, but this should load. Now you'll notice the first command I have here is to create a naive model. The naive model starts as a linear model predicting weight, and then we also have the tilde1. This connects the y and the x right here. So this is y tilde x, and the x is 1 because it's the naive. This just creates the naive model, and then we have to tell it our data because all of these variables are stored inside of a data frame. We're only really focusing on the y variable, and then we're just letting it build a naive model. So this will create a naive model. So you see the naive model created. Next, we want to create a full model. And a full model is a model that has all the variables in it. So you notice I still have my y variable being weight, and I have my dot for my x, which means all of the x variables. So when I create this right here for the full model, you'll see the full model appear, and the full model has all of the x's available to it. So it has everything inside of it. Now comes the step command, and this is the new thing for us here. We are storing the step function into something. We're creating something called s. And let's read through the command very carefully. Using the step function, we will start with the naive. Now, this is something you can change right here. If you want to change where you're starting, you could go to full, and that would change the starting point. This is just the starting point where you're telling it, start with this model. You won't actually change the scope equals list. This just creates a list of models for it to go through, and you do want the lower to always be the naive and the upper to always be the full. That is if you're searching through the list of models from the naive, which is no x's inside the model, all the way up to the full, which is all of the x's you have available. You can set different fences for your model. You could say the lower is a model with 2 variables in it, or the full is a model with 20 out of your 30 variables. But you always want the lower to be the one with fewer and the upper to be the one with more because it's going to search through. Those are the models it's going to look through available. That won't control where it starts. The naive right here at the moment is where it starts. If I change this to full, then it would start with the full, but I can't go forward with the full. I would need to go backwards. I could also go both ways. I could go forward and backwards, but the direction here controls which way we move when we search through the models. Just make sure if you have the full starting point, you would either need to go both or backwards. You can't go forwards from the full model. And also, if you start with the naive, you can't go backwards. So if I had backwards here, I couldn't have the naive to start. So that's very important right there, that as you choose to go through this. Now, if you notice, this is still one line of code. I just want to call attention to that this is one line of code right here. I just thought it looked nicer if I broke it up. When I run this line, it'll read through the comma and continue on to the next line. So this is all one line of code just running. So the data is from survey 10. We're still using survey 10. And also we have the trace 1, which means it's going to show what happens on here. So let's go ahead and run this and see what happens. Now it just floods the screen with text, so that's all very quick. If I had turned trace equals to 0, it would not flood the screen with text. And if you're doing any assignments, do not have the trace on. That's a very important thing because you'll turn in sometimes 50 pages of text and we don't want that. So let's scroll back up and see what happened when we ran the command. Now what a search procedure is going to do is it's going to look at the inclusion or exclusion of variables depending on forwards, backwards, or both directions. And when it gets right here to the start, we will see we started with the naive. Now starting with the naive, we had the option to move forward only right now. So forward means the inclusion of new variables. And wow, one variable, desired weight, really helps our model get closer to the truth. And AIC is a measure of how close our model is to the truth, and that's all it's doing. All it's doing is a repetitive procedure, just an iterative process of every time gauging the AIC. We get to see nice stuff like the sums of squares, which is the reduction in sums of squares. And so we have the reduction in sums of squares right there, and we see the AIC. But with that in mind, this is only focusing on AIC. That's how it is ordering these models. And that is related to the sums of squared error. So we're pretty much just focusing in on AIC, at least the way this is working, but there's analogous relationships to the sums of squared errors. So all it does is figure out which variable, for the way we're doing it right now, will lower the AIC the most. The first time it decided that desired weight lowers the AIC the most. Then it put desired weight in the model and it said, okay, gender lowers it the most. And it's always the top one right here is its decision. That's what it's choosing, but it lets you see what else it was looking at. And due to multicollinearity, if you notice, the list does move around. We see more athletic, height, and more attractive, attractive, and height. And you see the little change around right there. And now we see attractive, height, own attractiveness, and wow, totally switched. Those attractive went down on the list. And once again, when you put something in a model, it changes the model and it changes what might need to be included next. So every time we're doing this, this list here is changing. It's not simply moving in an order. That'd be too easy. Every time you put something in the model changes, and what should go in the model next depends. The model, every variable and every coefficient is model dependent. Sorry, just had to clear my throat right there. And so as we move down through the list, it'll finally get to the very end where we see the choice is none. This is where it stops when it's like, okay, there's nothing else to do. So now we have our model, and you can see the model right here. It's a quite a big model. There we go. And there's the final AIC of the model. So there's the AIC of your end model, and here is the formula for your end model. But guess what? There's an easy way to type in the formula. To type in the formula, we can just run this right here. If you notice, I have this command, $terms data equals survey 10, and this is my first model created from the step function, and you can see the same thing with all the variables. And be careful though, you'll notice in the formula we have gender, and a lot of times people, especially here with the build model you'll see later on, it might report things like gender male, but gender is in here. Gender male is the indicator variable, because there's gender female and gender male. So gender female is the reference level and gender male is the indicator. So don't be like, oh wait, my model doesn't have gender. It does have gender because it included gender male, and thus gender female is included as the reference level and the variable gender is in there. So there we go. That is how to use the step function, just a little bit right there. Next, let's look at making a predictive model. So we just did a descriptive model looking at AIC. But now it's time to look at a predictive model. And to do a predictive model, we need a training and holdout data set. So to make the training data, we're just going to, let's look at this command. We are going to make a vector of train rows. That's what I'm making right here. It's just a vector. You'll see it over here. And this vector is going to sample the numbers 1 through how many rows we have. So that's what we have. There's just a total of how many rows. We're in survey 10, sorry about that. Just a total of the number of how many rows. And then we have, once again, we are just choosing a percent. So from the percent, we chose 70%, which is going to be 489 total rows selected. So this command reads, select from the numbers 1 through how many rows there are in survey 10, just take from those numbers, and take 70% of those rows, because it's going to take 489, which is 70% of, I believe, 699. But if you want, you can always check, highlight a command, and hit Control-Enter. And so that is 70% of that. So when I make this train data right here, you can see that the train data has 489. That's the same thing we got down here, and that's why the train data has it. The train data is going to survey 10, which is just a data frame, and it is taking the train rows for the rows. We are taking all the columns. The complement, the other half of it, not half literally, but the other side of it is going to happen here where I take everything but the train rows. I'm going to take not the train rows for the holdout. And you'll notice over here, 210 plus 49 is the total 699. So I've sectioned off a training and holdout data set. This is because when we make a predictive model, we need to know how it works on new data. We must say, how does our model work on new data? And the only way to figure this out is to build it on one section of data and then see how it works on new data that the model was not created from. As you can see in this command right here, in the build model command, we're going to do an exhaustive procedure. So watch out, because if you do this procedure, and this goes to the all possible models, which we also use for descriptive in some instances, you are searching through all possible. So my computer freaks out a little bit, but I've got a pretty good Core i7 processor, and it can handle 20 predictors. That's it. It's freaking out over 20 predictors. So let's see, and I will say this also, if you have categoricals, which luckily I don't think I have many categoricals with tons of levels, but those will often create a ton of possible ways to do it, because they eat up your degrees of freedom pretty quickly. But I can handle this. Let's let it run for a second. 3, 2, 1, model. There we go. I've ran this before, as you can tell. I just wanted to make sure nothing blew up while I did this example. And let me pull up the graphic right here, and let's talk about what we have. So here's my graphic. The naive model is way up here. The naive model would be the one with no variables. And luckily for us, we can actually predict weight with some sort of error that's better than the naive, because the naive is way up there. We can't even see it. So this is the estimated generalization error. Of the 3 generalization errors we talk about, or the 3 errors we talk about, this is the middle one. We have how our model works on the data it was created from. We have how our model is expected to work on new data, which is this one. And then we have how our model actually works on new data. So this graphic is displaying how we estimate our model will work on new data, which is the middle one, the RMSE validation. It's very important right there. So with the RMSE validation, we would get different results through the k-fold cross-validation process. And if I change this seed here, which controls the randomness for the k-fold cross-validation process, I will get different results. So if you watch my graphic, the graphic will change slightly, and if you notice, it shifted. Those little bars shift. If you rewind and watch again, we'll do it with a different seed here, and you can actually get different models when you do this. I highly doubt I'd get the naive because desired weight is so good at predicting, but I've done this a few times, and sometimes I actually get gender or stuff like that. It just depends on the k-fold cross-validation process, which is a randomness procedure. And you might need to go back and review. I'm trying to get a different model, but I wanted to display something other than the model with one variable, which is weight, desired weight. And let's cross our fingers. Nope. It's loving that weight desired weight formula. If you notice, we get a formula with a lot more in it. But when you look at the graphic, that's this one right here, which we have some uncertainty on how this works. This is one standard deviation of uncertainty. So we're saying this is my best. It's expected to work with an RMSE of about 18, which we typically miss someone's weight by about 18 pounds. But if we just use the one variable model, we'll typically miss by about 19. And the uncertainty for the 9 variable model is an uncertainty of, that's a lot of uncertainty, about 2.3. And we can confirm these numbers if we go back through the commands right here. Let's just go ahead and do a list command right here. Put it after the build model. And let's go to the CV table. Okay, so here we are, and we have our, let's look at this, the estimate squared generalization error, the estimated generalization error right here, and let's go down. So they're doing the squared to start, so we can use these errors right here. This is the one we're actually looking at in the plot right here. If you look over at the plot, we get 18 right here, and then we have the squared. So when we go over here and look at the commands right here, you'll look at this right here. So 322. 322 is the squared estimated generalization error. Then when you look at 322 and you have the standard deviation, this relates to this one right here. Of course, we usually don't talk in squared units. That's why the chart just gives the estimated generalization error. But the standard deviation is related to this one right here, and I can show you why. One, because if we had a standard deviation of 88, we'd definitely be using the naive because the naive is within one standard deviation, but that's not the right units. We need to add the 88 right here, and that is about 410. The decimal change is definitely about 410. If I'm doing, actually it's 4, is it 410? I am doing it right in my head. And if you're confused, let's just do the math ourselves. What we're gonna do is we're gonna take the standard deviation, and let's take the estimate, and we'll have to scroll back up after we do this, but it should be about 410. We are correct, it is 410. And what that means is anything that is below 410 works about the same, at least so much that we can't tell how different it is. We're like, well, they're basically the same, such that maybe we should select a simpler model. So going off of Occam's razor, that if things are simpler and they have about the same explanatory power, simpler is probably better. And wow, one variable really does it. And we saw this 19, which that same 19 is the 19 you see right here. And that is what you're seeing with your estimated generalization error. So we think, this is what we think it'll do for new data. But you know what? We can do it. We can check it out. And just so we can see real quick, this is how it works on our current data set. And now let's go ahead and run this here. If you notice, it did a little bit of rounding, and I think Dr. Petrie has this formulating a tiny bit differently. This was created from the trained data. I want to make that clear. And here we go right here. Wow. On the holdout, wow. It actually does better. It actually does better. Which we'll see right here in the final command. This means that the training over the holdout has and let me reverse that, the holdout over the training, because it often makes your mind confused. This is not overfitting at all. This is actually doing way better on the holdout than it is on the train. It makes a typical miss of about 15 on the holdout, and on the train, it makes a miss of 19.2. And I just believe the way Dr. Petrie is finding it for his command might be a little different than the way the summary command is finding it, which is just the general regression used in the program. But you'll notice here, neither of these were this 19.08. This 19.08 or 19.09 rounded would actually be the one between these two numbers, this 19.09. It is how we think it'll work on new data. So we actually did better than we thought it would work. So there's three RMSEs, the RMSE train, the RMSE validation, and the RMSE holdout. How it does on the data it was created from, the one in the middle that we can't see right now, how we think it will do on new data through the k-fold cross-validation process, review that in the notes, and then also we have how it actually does on new data. How it actually does is the RMSE holdout, and that's how it does on new data. So let's look right here. One other thing I want to mention is the way the train rows were created, you can actually put a set seed before that because, and let's put 470. I'm putting some high-level class numbers on this. When you run this, oh, I did not put my semicolon. That's why I wrote out most of my commands beforehand. You always forget one little thing. That runs two commands on one line right here, putting the semicolon. So I immediately ran a set seed. And what you'll notice now is if we'll show it with and without the set seed. Because the ways I create my train and holdout, let's just do this. We'll print the train. And if you notice, it says 510 right here. And if I run this again, and then I take a look at my train, it'll say 510. But if I just run train rows here and create the training again, and I recreate this right here, I don't get 510. Now, watch this. Do I want to see 510 again? I'm going to run set seed, which will do the same randomness every time. I'm going to recreate my training. And I think the first time it's 496. Now here's where I made a mistake. It's actually going to be 496 again because I didn't recreate my training. I was working off my old training. Every time I run this command now, I will get this. But, and let me rerun where I make my training. So there's me making my training again, and I get 496 every time. But if you take away the set seed, and let's just run it as a series of commands. I'll tell you what, the easiest way to make sure everyone knows exactly what I'm doing right now is I'm going to put all commands in sequence right here. Just want to review some key topics I want everyone to know. Okay, so here's what we're going to do. We're going to run it with the set seed, then we're going to create the train rows, and then we're going to look at the train rows, 496. But if you don't have a set seed, you create your train rows, you create your train data set, and then you look at your train and it's 492. You do the same thing and it's 211, and you do the same thing and it's 247. If you notice, every time I do this without the set seed, I get a different last row. That's the row number right here. You're seeing 499. So that it's a different row every time. But when I do it with a set seed, same. I can just keep running this over and over again. I'll always get the same exact thing because it's going to do the randomness the same way till I don't use a set seed and I get different ones right here. And actually, what you might notice if you really paid attention, like watched very, very carefully, is it's actually going to repeat the same sequence of n rows after the set seed, because the seed has been set for the randomness. So the next series of what it would do, it's very interesting actually, but I am not getting the same thing unless I reset the seed and I say start with this seed again at the very beginning of the seed. But once again, I want to make very clear what you should know 100% is that when you run the set seed on your train rows at the start, you will get the same exact result every time. So I'm getting 496 every single time. So this is often used in assignments, or if you want to replicate your results, because I'll always get the same thing after I run the set seed. I know exactly what I'm going to get if I've already seen it once. I don't know what I'm going to get before I run it because it is still randomness. But I get, it's like, picking a bingo card and saying, this is the card we're going to play bingo with. That card was picked randomly, but once you look at the card, you know what's on it. And then you can say, okay, card 40 is random, or in this case, card 470 is random, but we know what's on it. These rows that I have are random, but I know what the rows are. And I think that's got it. A little bit of a longer video than I thought I would do, but I wanted to review some key concepts and make sure you know what's going on. Good luck.